So, in your talk, so please start. You have something like 55 minutes and then the question.
Okay, great. Thank you. Well, so first of all, I'd like to thank Professor Lewandowski for the invitation to talk. And secondly, please feel free to interrupt me in case you have questions in the middle of the talk. So today I would like to talk to you about some of the projects I have explored during my PhD at the Jagiellonian University. And it's mainly in the scope of theoretical and phenomenological cosmology and within early universe and gravitational wave physics. So first of all, I'll give a brief motivation to these investigations we've made. And then I'm going to talk about first two of the results that I consider more impactful, which are the first one, so this one and this one. And then after that, I'm going to briefly mention some other results in other directions that we had, which are those three parts here. And after each of these sections, I will give a brief summary, and of course, we can come back to it in case you would like to check it also at the end of the talk. So we know that Lambda-CDM is a very successful model to describe cosmology. On large scales, cold dark matter describes the data very well. We know that for now, a cosmological constant seems to be the best option for dark energy. But although this Lambda-CDM is still the best model that we have for now, and we are not able to replace it with anything else, there are some problems or unclear aspects of these scenarios that still have to be investigated and solved. So here I mainly focus on the problem of the initial singularity, origin of cosmological perturbations, CMB anomalies on large scales, nature of dark energy, and dark matter. And of course, there are other issues, such as like the Hubble tension or the sigma H tension, which are also problematic, but I'm not going to approach them in this talk. So our main motivation is to investigate those first 5 issues that I mentioned. And in each of these projects, we approach it either one or a couple of them. So the first project that I would like to talk about is this investigation about CMB's imprints that come from quantum cosmology or bounce cosmologies. So first of all, I'd like to talk about the so-called CMB anomalies on large scales, which are very anomalous features. So they are features that appear in the data, and they have a very low probability of happening within Lambda-CDM. And they are usually quantified by means of the so-called p-values. And the p-values for each of these features is smaller than 1%. So this means that they have around 1% of chance of appearing in the data given Lambda-CDM. So it's a very small probability. Although they don't have very high significances by means of like sigma, they are usually around 2 sigma, 3 sigma, they are still weird because they keep appearing in many different surveys. So the first one of them is the power suppression, which is the absence of a 2-point correlation function when you look in the sky to the CMB temperature map, which means that when you correlate to different points in the sky, you get an absence, a suppression of those 2-point correlations on angular scales that are larger than 60 degrees. And then we quantify this by means of this estimator as half, and this is what we observe, and this is what is expected by Lambda-CDM, so it's very different. And it only happens on very large scales, larger than 60 degrees. On small scales, everything is consistent with Lambda-CDM. Then the second one is the parity asymmetry, which is an issue that appears when you consider the temperature as a field, and then you analyze the parity properties of the temperature field. And then you can translate the odd or even parity to odd or even multiples in the CMB because of the properties of the spherical harmonics. And here we have this estimator that quantifies, here it's something related to the power spectrum of even multiples, and this one to odd multiples. And then in the data, we see something that is smaller than 1, which indicates that there is an odd parity preference, which is different than the neutral parity that is expected by Lambda-CDM. So this is the second anomaly. The third anomaly is this dipolar anomaly here, which means that when you look into the data at the CMB, you have, and you compute a bipolar spherical harmonic, you see something that is not 0. And this indicates that there is a kind of a dipolar modulation in the data on very large scales, which is also something that we cannot explain with Lambda-CDM because we would expect it to be 0 in an isotropic universe. So these are weird features. And then, yes. Yeah, that's true. So all of them have cosmic variance, which is this intrinsic error that you cannot get rid of. And this is the most challenging part to observe these anomalies. And that's why people still think that it could be just a statistical fluke or some new physics. So there are these two different point of views. And but we are going to see how we were able to use Planck data and still surpass cosmic variance and get an insight into these anomalies. But you are right. Yeah, so these anomalies appear in the data, so regardless of any scenario. So even if you assume Lambda-CDM or some inflationary exotic model, the issue is still in the data. Yeah, so these bounce scenarios are one of the possibilities to, in principle, alleviate these anomalies. So that's why I'm going to talk about the bounce. So I would like to explain first what are the anomalies, and now how these bounce scenarios are able to alleviate them. But they are considered like exotic physics. It will be new physics on large scales. But for standard physics, these anomalies are weird for any scenario. So there is this bounce scenario that was proposed by Agulo, Kronos, and Srinath, which is a very interesting idea. So they tried to keep it model agnostic. So they first did these computations in the case of loop quantum cosmology with this type of scale factor, and here with 1/6. And then they decided to generalize it to consider other theories that might lead to this very typical scale factor for a bounce. And then they keep this parameter n and b, which are just numbers related to the theory, and this b will be related to the curvature at the bounce. And then what happens is that they show that this might lead also to an inflationary phase after the bounce. So in this case, they have both situations. They do have the bounce and they have inflation after it. So what happens is that the initial condition, so like the adiabatic vacuum, will be now placed at -infinity, as it's usual for bounce cosmologies. And then at the onset of inflation, these perturbations evolve, and they are not in Bunch-Davies vacuum anymore, so they get non-Gaussianities. And these non-Gaussianities are going to relate to different modes. So if you have non-Gaussianities that are very large, only on very large scales, then you're able to relate modes that are super horizon to modes that are inside the horizon. So in some sense, you start to have access to physics outside the horizon because they impact the modes that you have inside. And then if you consider a spectator mode in the sense that it's not statistical, so you consider a concrete realization of this field outside the horizon, and it will be correlated to the modes inside the horizon because of the non-Gaussianity, then it creates what is called a monopolar modulation in the data. So this here is the CMB power spectrum. And then we have, this is the usual contribution. And then when you have this spectator field outside the horizon, you have this type of modulation contribution to this observable CL because of the non-Gaussianity. And then we consider this to be, has a distribution with a zero mean, and then with this variance here. And then these are quantities related to CMB, like this is the CMB power spectrum, this is the primordial power spectrum, and this is a quantity that is a very ugly expression, but the important thing is that it's proportional to FNL. And this FNL is a parameter that quantifies the strength of the non-Gaussianity that you have. So it means if you have a very large non-Gaussianity, then you have a very high FNL here, and then this variance will be very large. So this means that the mean to get the usual power spectrum from Lambda-CDM is the same. So at mean, it's still isotropic with all the properties of Lambda-CDM. But because it has a larger variance, you increase the probability that you get those anomalous features. So you can require a value of FNL that will be the one that makes these features appear, for instance, with 20% probability instead of 1%. So this was their idea.
That's kind of and waiting argument why with no Gaussianity you might present the large scale and no
Yeah.
That observational bounds, observational bounds on the small scale.
Exactly.
Right?
Yes, exactly. So this is a very interesting property specific of these scenarios, because we are going to see that this bispectrum here has an exponential decay. So it means that even though you have very large non-Gaussianities on very large scales and outside the horizon, inside the horizon, they decay very rapidly. So this was their main point. So if you pick the pivot scale to be the bounce scale, this makes these non-Gaussianity decays very fast in scales that are observable in principle. So this was the main idea behind it. And this only happens because you have this bounce before inflation. So they consider those two different scenarios. This one would be loop quantum cosmology, and this one is a phenomenological bounce, which is the one that best fits the data. So it fits the data even better than Lambda-CDM, which is quite remarkable. And then these lambda and Q are just related to the parameter n. And here we have two columns for FNL. So here we have, because it depends on the curvature that you have for the bounce. So here we see that we have very, very large values for the possible FNLs, and these are the values required to make the power suppression anomaly happen with 20% probability. So this is the values that they used in their work, and the ones that we are going to keep for the first part of the talk. And then here we have the power spectrum, and because now we have bounce and inflation, we have two different scales for the scenario. So it splits the power spectrum in three different regions, where this one will be the usual almost scale invariant one, and these ones are the weird behavioral scales. But in principle, if you set the pivot scale of the CMB here at the bounce scale, then all this behavior here should not show up in the data. So this was their main idea. And here we have the bispectrum, which you can compute from this primordial power spectrum here. And then what Vanagulu and collaborators did was to keep it in the model agnostic way. So they use arguments that are valid for most theories, most bouncing cosmologies, to show that you get this exponential suppression here for this bispectrum. And then they also check it for specific scenarios such as loop quantum cosmology, and they also get this exponential suppression here. Well, here K1, K2, and K3 are just the three modes that form the triangle for the non-Gaussianity, and the KB here is the scale of the bounce, which is the one here, which, if I remember correctly, was 0.02. And then they were very successful in addressing the anomalies with these modifications. So here we see that they alleviate the power suppression anomaly as they require. So they can achieve with 20% probability something that is consistent with the data. And then for granted, they also solved the dipolar one and the parity asymmetry one. So they were able to alleviate all these anomalies at once, which seems like a very interesting phenomenological result of these specific scenarios. And then when they checked also this lensing parameter, so this lensing parameter is a parameter in the Planck analysis that is a parameter just put there for consistency check. So you just keep it as a free parameter. And then when you feed to the data, you should recover one if everything is consistent. And then for Lambda-CDM, they get something weird, which is a bit different than one. So the blue curve here, which is 2 sigma away from one. And then with these scenarios, they approach one. So they also alleviate this lensing anomaly issue in the Planck data. So it was a very interesting phenomenological scenario. So we decided to just check if we could find imprints from this scenario in the Planck data. And we computed this quantity here, which is the reduced bispectrum. So this is the quantity that we actually observe. And then it can be computed within linear perturbation theory by this expression here, where this is just a dummy variable. And here we have the so-called transfer function, where on very large scales, we can approximate it. If you only consider the Sachs-Wolf plateau, you can approximate it by this expression, where T0 is the time today and T decoupling is the time at the CMB decoupler. And this is a spherical Bessel function, as well as this one. And this bispectrum is the one from the previous slide, so a very weird expression with an exponential decay and so on. So these integrations here are impossible to perform analytically. So we did it numerically, and even numerically, it's quite challenging. So what we realize is that when you have the product of those two spherical Bessel functions here, they will interfere constructively. So they will create a peak. And then in the other regions where this argument is not the same as this one, they will interact destructively. So we just disconsider. So we just integrate around those peaks here. And then we do that, and then we obtain these dark blue dots, which are these reduced bispectrum for the bound scenarios, and the black line is just a fit to it. But what we want to see is whether we can find some imprint in the Planck data. So we need to compute the signal to noise ratio, and then we consider 70% of sky coverage because it's the Planck experiment coverage. And then we compute cosmic variance, which is related to this signal, which is the reduced bispectrum. It's given by this expression here, where these are the CMB power spectrum. And then we have here the expression for the signal to noise ratio. And for now, we don't have experimental noise, just cosmic variance, because as you mentioned, it's a very significant contribution on very large scales. And then here in this plot, we can see that we have the blue dots, which are the bispectrum. Here in black, we have the local bispectrum, which is already very well constrained by Planck. And here in gray, we have cosmic variance. So what we see is that although this bispectrum is larger than the local bispectrum, which is already very well constrained, cosmic variance is larger. So it seems, at least at first glance, that this would be indeed hidden in the data. But what happens is that if you fit a curve to those points, you see that for those very low multiples that you have here, this fit will surpass cosmic variance. And because we are considering cumulative signal to noise ratio, you keep summing over it many and many times, and this contribution starts to make the signal to noise ratio very large. So when we computed it, this is the case for loop quantum cosmology, is larger than 25. And then for the phenomenological bounce, if I remember correctly, it was even larger. So this should be detectable in the Planck data. And then at this point, we thought that it's possible that people just haven't looked into this template yet, because the inner product of this template and the standard shapes, like a local shape or orthogonal equilateral shapes, is very small. So no one has looked into this shape in the data yet. So we decided to do it. And then in order to do that, we went a few steps back, because before we used that approximation for the transfer function on very large scales by considering just the Sachs-Wolf plateau in the CMB power spectrum. But now, because we want to compare with the data, we decided to do everything numerical. So we used the Boltzmann codes. You could use either COMB or class, and then just compute the full numerical transfer function. And here we see that for the multiple 2, which is the one that most contributes to the signal to noise ratio, you have this difference between the class transfer function, which is the fully numerical one, and the approximation of the analytical transfer function that we used before. So we correct for this and then compute it again. And here we have the dark blue dots, which are the results with the full numerical transfer function. And here this cyan line, I don't know if you can see it well. It's the fit that we had previously with the approximated transfer function. And here we see that it surpasses a bit, it overestimates a bit the bispectrum, but in the end, it was not a problem because the signal to noise ratio was still large enough to be detected. And here, just for comparison, we have the local bispectrum, everything with FNL1, so normalized by FNL, just for comparison of shapes. So we see that it's similar in shape to the local bispectrum, but in the case much quicker. So that's why the inner product is so small. And then we used this FNL estimator here, which is given by those inner products between the theoretical bispectrum and observational one, normalized by the theoretical with theoretical, defined in this way. And then you can also compute the Fisher matrix, compute the correlations, and so on. And then we see here that indeed, the bouncing scenarios, this is the one for loop quantum cosmology, this is the phenomenological one. They have very low overlap with the local equilateral and orthogonal. And these are the noise sources that we have in the data, which also have very tiny overlap with this bispectrum. This is cosmic infrared background. And the only significant overlap, of course, is between the two different bounce scenarios, which is 0.91. And then by using Fisher analysis, what we found was that this FNL would be fitted as those two values, this one for loop quantum cosmology, this one for the phenomenological bounds. And this is the 1 sigma error. So if you compare these sigma errors to the values, the very high values of FNL that we had on large scales, we see that they are excluded by 6.4 sigma and 14 sigma respectively, which are very high significances. So this means that although these scenarios have this very fast decay inside the horizon, and it was believed for some time in the literature that they could not be excluded, we can use Planck data and they are excluded with very high significances. It does not mean that loop quantum cosmology is excluded or any other bounce cosmology is excluded. It means that they cannot solve the anomaly. And this is also valid probably to also scenarios that try to alleviate the anomalies by using some skewed statistics, similarly to what they've done. So it's not only restricted to bounce cosmologies. And then the similar very high significances for exclusion are found for different values of N or Q, which means different models. So we also consider all possible models that could alleviate the anomalies, and they are also all excluded. And then we decided to then reduce the p-value from 20% to 10% and then 5%. And then what we saw is that they are still excluded. And then if you reduce it like to 5%, it's still excluded. And it's not even much better than Lambda-CDM, which makes 1%. And I think the two main points of this work is that it shows the sensitivity of the Planck data in scales that go beyond the pivot scale. So it's not as if it's impossible to test physics on very large scales. We can still make it with data that we already have. And this is a very good tool that we can use to test quantum cosmology scenarios or physics that we thought it wouldn't be observable nowadays. So this is the first part of the talk.
So, what I do. So suppose that I come up with some new quantum model of linear, I can see that there is a bound in this model. So what should I check in my model to know whether it is simplified over or whether it is not?
And so I would say mainly the non-Gaussianity, which in principle you can pick the value of FNL that you want. So we cannot have very large non-Gaussianities. Well, not larger than this type of non-Gaussianities. So you need to compute, well, if you have the primordial power spectrum computed from your scenario.
Okay. So my point of view, what I can do is I could consider some model of space-time, and then, okay, if I'm very ambitious, then I will do all the trinity, is not very significant, the usual classical, the usual human level of the model, but it is quantum space, which some quantum theory, and I can go with the classical lineage, and I can use some classical space-time inversion theory and the space-time part. Okay, and given that, what should I do?
Yeah, so if you're not interested in alleviating the anomalies, you are fine, because then you don't need the high non-Gaussianities, because like it's not as if this bispectrum only appears, so this one. This appears for general models, so general bouncing cosmology. Yeah, so, but usually we model the non-Gaussianity by considering, let's say, a Gaussian field at linear order, and then you introduce a term like plus FNL, and then potential squared. FNL is this parameter, which is a number that you put it with inside, in front of the nonlinear contribution of your Bardeen potentials, which are Gaussian. But when you have quadratic Bardeen potentials, then they form this non-Gaussianity that correlates different modes. The gravitational potentials. Yes. So if you consider a Gaussian theory, you only have, let's say, psi. And then if you have non-Gaussianity, you can consider this specific model, which is the most common one, which is the psi plus, and then FNL, which is a number, times psi squared. And then this psi squared is the non-Gaussianity. So the thing that FNL that is in front of it quantifies how strong this non-Gaussianity is. And in principle, you don't get it from theoretical predictions. You only have this FNL, and then you can fit this number based on the data. So if you are not interested in solving the CMB anomalies, then your scenario is okay. Nothing is excluded. If you are interested in alleviating the anomalies, then you cannot do it in this way because all of them are excluded. Because then they pick FNLs that are high enough so that the anomalies are alleviated.
Could you actually give some kind of again, a simple physical argument why you expect no Gaussianity in the basketball? Because, in the standard model, I understand why it's Gauss, right? I'm just saying that, my fluctuations are different to wavelength are completely independent, which is essentially what you have for the project in particular. Now, could you explain why and how natural you that you have a bound model, you have some natural methods predicting the.
Yeah, so if you only have the bounce, then it's not the case of this approach. It's possible that you don't have non-Gaussianity. It will depend on the bounce scenario. But if you have bounce and inflation later, then what happens is that you have the vacuum initial conditions at minus infinity for the bounce. But when it reaches inflation, it already excited to something else. And this generates the non-Gaussianities. So it comes from the fact that they have both a bounce and an inflationary phase. Yeah. If they don't have that, then it's possible that the non-Gaussianity is just small. No, here is bounce and inflation. And that's why they have this non-Gaussianity that decays exponentially. And that in principle could solve the anomalies, but as we've seen, it can't. But so they try to keep it model agnostic. So the scale factor, which is this one, there are people that work with loop quantum cosmology in general. So this investigation started with loop quantum cosmology bounce, but then later they decided to just keep it general with this parameter n, so that you could recover other scenarios as well. Because at this point, the fundamental physics that generated the bounce is not any more important. So what matters is what kind of scale factor you have, what power spectrum, and what bispectrum. And then they saw that it's kind of general if you have this type of scale factor.
Based on these scale factors,
what yeah.
Scale you have between rewrite to this scale factor.
Yeah, so there are different fundamental theories that give rise to this scale factor. And then we analyzed all of the possible ones just by switching n. And then what we find is that all of them are excluded, including the loop quantum cosmology one. So unfortunately, it cannot solve the anomalies.
So this is for flat cosmologies, right? So with k equal to 0.
Yes.
So the scale factor would change with flat k equal to 1.
Yes, if you want to consider extra modifications, then it's possible that you can find a way to evade the constraints. So I know that after we published this work, there were people that consider oscillations here on top of this exponential decay, and then they see that then it would be fine with the Planck data, but they haven't analyzed yet whether this alleviates the anomalies, but it's possible. So it will be a way out, but it's not confirmed yet. So for the second part, I would like to talk about another direction that I've approached, which is gravitational wave resonance. So first, this case is within ultralight dark matter halos, and it will lead to the amplification of the gravitational wave. So here in the left-hand side, we have a normal oscillator, which all of us have seen at some point, where A is just some number related to the dynamics of this oscillator. Here I kept it as 1. And then in the right-hand side, we have this weird oscillator that amplifies with time. And the only difference is the addition of this term, which is a periodically varying mass term. And this creates this behavior, and this equation is the so-called Matthew equation. And we can analyze it by means of the Floquet instability theory. And then in this case here, I just wrote the Matthew equation as two separate differential equations, and then resolved for the fundamental matrix of solutions. And then you can plot this type of diagram where this is the parameter A. So from this equation of motion, we have A and Q, which are just parameters, just numbers. And then you can plot A and Q. And here the real part of the parameter mu, which is the so-called Floquet exponent. And this is the parameter that quantifies how much this oscillator can be amplified. So here we have, this is the solution predicted by Floquet instability theory for this oscillator, which is an exponential of this mu parameter here times t. So the higher the mu parameter you have, the higher is the amplification of your oscillator. And then here we see those deep blue regions where it's just zero, so there's no amplification at all. And we have these colored regions, which are the so-called resonance bands. So we call it like first, second, third, fourth, and so on, the resonance bands, and they are centered around 1, 4, 9, and so on. And within these resonance bands, we have amplification of the oscillator. And then if this parameter Q is much smaller than 1, we are in the case that we know as narrow band resonance. And here we have the behavior of mu depending on Q and Q squared. So if you are in the first band, which is this small part here, then it goes in this way. And then if you are in the second band, which is the small here, it goes as this. So in the case of gravitational waves, we are going to see that this parameter is much smaller than 1, which means that we are in narrow band resonance. So the most efficient amplification can be achieved if we are in this small region here. So now I'd like to motivate why to consider ultralight dark matter as dark matter candidates. So we know that on very large scales, cold dark matter describes the data very well, especially CMB data, for instance. But on small scales, there are some incompatibilities between simulations that consider cold dark matter and the data. So the main difference is that for cold dark matter, we have these cusps, which are those peaks in the center of the halo. And then what we observe in the data are these cores. And these cores, they are formed by those ultralight dark matter candidates because they are so light that they have a de Broglie wavelength related to it, and they form a Bose-Einstein condensate. And then they form a kind of a Jeans scale, similar to what we have in cosmology. And then beyond this Jeans scale, these perturbations are suppressed. So this makes this formation of those cores instead of the cusps. So they are very interesting candidates to investigate this type of incompatibility in the data. So let us consider that we have a halo described in this way here, where here we have the gravitational potentials, and they are always much smaller than 1, even inside the halo itself. So we can treat them perturbatively. And here we have the axion, where now I only consider the ground state. So we only have this dependence on time. And here in the non-relativistic limit, we have that the frequency will be the mass of this ultralight particle. And then from this scalar field, which is an axion, we compute the energy density and pressure. And then we see here that we have a constant energy density. This is the amplitude, which is constant. And here we have a pressure with very interesting behavior. So we see that it oscillates, and it oscillates around 0. So that's why it can be treated as dark matter. Because on average, it will be 0, like a pressureless fluid. But then we have these oscillating parts that are nevertheless still there. And they cause modifications. For instance, here's the trace of the energy momentum tensor, the two potentials that we have, and the rich scalar, which is this expression here. So here we have the 0 parts, which do not depend on time. And these are the parts that oscillate in time. So here we see that these gravitational potentials oscillate in time. So from the Einstein equations, we get that the U0 bar and U0 are the same. We also get this type of Poisson equation, which we can use to estimate the size of the U0 part, which will be this whole here, which is the density, over Ka squared, where Ka is the wave number of the axion. And we can also get this type of equations by using some approximations and get the expressions for delta U bar and delta U, which are the oscillating parts of these gravitational potentials. And this is very interesting from the perspective of resonance, because we've seen that if you have a periodically varying mass term in the equation of motion, then you might lead to an amplification of something. So if we consider, remember that gravity bends gravity itself, and we use the tools that are already used in gravitational wave lensing, we can split the gravitational wave in an amplitude and here the polarization tensor. So this polarization tensor here, it does not play a role in gravitational wave lensing because it only appears at higher order. So we can neglect it for now. And then just write this equation of motion for this scalar part of the gravitational wave. And then what happens is that here we have the G mu nu and the determinant, and here we have the gravitational wave. But we know that inside these parts here, we have the oscillating gravitational potentials. So if you expand this equation of motion, then you might get a coupling between the gravitational wave and the oscillating gravitational potentials in such a way that you create a periodically varying mass term. So this type of perturbation. Yeah. So then I decided to expand this equation. So here we have those couplings between U and H, which are the things that we are interested in. And for now, it doesn't look like a Matthew equation because we have those friction terms. But then we can make these redefinitions here. So this is dimensionless time, the mass times time. And this H bar is just redefined in this way, in such a way that we kill those terms. And then we end up, well, if you go to Fourier space, then you end up with this equation here, where here we have this convolution, which might be complicated to perform analytically because you have a spatial dependence here. But then if you pay attention that this U0 is proportional to this quantity here, and it's compared to something that is just k square over m square, and this is much smaller than 1, so that the gravitational potentials are also much smaller than 1, you can neglect this term. So you can approximate this A parameter of this Matthew equation by this quantity here. And then if you do that, you end up with an equation if it's exactly the same as the Matthew equation that I showed before. So where here this Q is this quantity, and this is proportional to the gravitational potential. So by definition, it's always much smaller than 1. And this is the A. So if this is much smaller than 1, it means that we want to be in the first resonance band so that we have the most efficient amplification. And then what happens is that then it means that the wave number of the gravitational wave will be the same as the axion mass. And then from the Floquet instability theory, we have this prediction of amplification, where here we just switch it back to the original gravitational wave instead of the gravitational wave bar, with this exponential factor that relates them, which is approximately 1. And then here we have this animation that shows this amplification that happens very quickly. Here it reaches 1 to 10. And then here I consider the fiducial mass for the axion field. And this density here is unrealistically large. I just put this prefactor here to reduce computational time. And this is the energy density in the solar region for this ultralight dark matter or any kind of dark matter that you consider. So here we see that there is indeed parametric resonance, which means that this gravitational wave will be amplified in time because of the oscillations of those gravitational potentials. But now we would like to see whether we can observe this parametric resonance. So we consider first that these axions constitute 100% of dark matter. We are going to see the constraints in a minute. And then this energy density here in the solar region, and this is the fiducial mass, which this fiducial mass is the one that is more efficient in solving the small scale incompatibilities, so the cusp and core issue. And then we see that it will take this time to have order 1 amplification, and this is larger than the age of the universe, so we are not interested in that. And what we need to do is to consider higher densities, because if you do that, then you get a higher parameter Q in the Matthew equation in such a way that you have a higher amplification. And these higher densities, they appear in different scenarios in the literature, usually related to the presence of a black hole inside the halo, because it creates those dark matter spikes. And then they can reach these high densities within the halo. So here we consider this density, which is the one required in order to have order one amplification for the fiducial mass here. So here we have this plot for the mass, and here the time in years. This is like a threshold to assure perturbativity. So this is the region where ρ over m squared is 0.01. So from this point here, it starts to get too big. So I would not consider this part of the plot, just the part on the right-hand side. And then we see that for the light masses, we have huge amplifications. And this is the argument that goes inside the exponential. So from 1 on, you already have significant amplification. And then for the higher masses, it's a bit more complicated, but it might reach order 1 if you wait 10 to 10 years. And this is a very large time, but it's compatible with halo formation time. So in principle, it could happen. And these masses here, if you remember that the wave number of the gravitational wave is the same as the axion mass, it will fall within PTA frequency range. So it could be possibly observed. For the other masses, there are no current observations from any gravitational wave source. So this will be the most interesting range for the observational purposes. And then we know that there are already many different constraints to those axions as dark matter because they have many different phenomenological implications. So here we have constraints from CMB and Bose and Spark, Eridanus 2, Lyman alpha, DES, and also some other implicit bounds because they are already considered here and they do not reduce further the parametric space here. So we see that it's very well constrained because here it's a log. So even in this window here, it's already constrained. So we can consider that instead of constituting 100% of dark matter, it could be a part of dark matter. And then if we do that, then we obtain this plot, which is of course a bit suppressed compared to the previous one because you have less dark matter to induce these gravitational potentials. But you can still reach significant amplifications for lower masses, especially lower masses, but this will be the most interesting range. So in this part, what I concluded is that these gravitational waves, they are amplified if you have ultralight dark matter as part or the totality of dark matter. And this will lead to the amplification of the gravitational wave. Nowadays, in order for this amplification to be observed, you have to consider a very high energy density, which appears usually in those dark matter spikes. And the sources for these gravitational waves are the ones in this frequency range. So it will be either primordial perturbations or supermassive black hole binaries. And the things that I would like to explore further is whether modified gravity that is like motivated for these specific axions as ultralight dark matter could boost the resonance, or also if you consider a gravitational wave background. Because for now, I only consider one single gravitational wave. And from Floquet instability theory, we know that there are some analyses that show that if you consider more sources, it will boost the resonance. And then finally, whether it would be possible to detect this resonance in the PTA range. So this is the second part of the talk.
What is the range of the gravitational wave vectors, the frequencies for the current one?
You mean for the ones that I can detect here?
No. What is the range of detection of gravitational wave for the current detector?
So for PTA, it would be this range here, like around 10 to minus 8 up to minus 9. For LIGO, it would be frequency of 100 hertz.
So it's about
yeah, much over than this one. So you couldn't see it with LIGO. Maybe with some other type of future experiment. But because these masses are very low, this frequency range here, that I don't know about any detector that is planned for the near future. So it would be mainly this region, which is the most interesting for PTA. This is by pulsar timing array. So like those pulsars that, like you have those photons that travel from the pulsars to Earth. And if you have a gravitational wave background, when this photon is passing, then the trajectory of the photon is perturbed. So you can detect the time delay from different pulsars. and see if they are correlated. Yeah, so it's, I won't say it's been detected, but like last year, there was a paper saying that they found gravitational wave spectrum. So they found a quadrupole, something that behaves like a gravitational wave background. And for now, they think that it's from supermassive black hole binaries. So apparently, they performed the first ever detection from a background. It's not apparently a primordial background, but it's still a gravitational wave background. No, so these are in this -8 to -9 hertz. So this is similar to this. Yeah. So now I would like to just mention some other results that are also shed some light into the Lambda-CDM or modified theories. And I would like to start from this one. It's the graviton to photon conversion, because it's related to the previous one, but it's the other way around. So instead of amplifying the gravitational wave, we wanted to check whether gravitational wave could be suppressed because of the interaction with an electromagnetic field. So we consider here the square root of F mu nu, and then you have just Minkowski background, but with a medium where speed of light is reduced. So that's why you have this eta tilde here with the CS, which is related to this reduced speed of light. And here the gravitational wave. And then we expand, and this is the I component of the equations. And in these equations also, we see that there are couplings between the F mu nu and the gravitational wave. So in a similar way, we can also get a Matthew equation. And then we consider this standing gravitational wave. You could also consider a traveling one. It works in a similar way in a medium. And then we perform these redefinitions of fields. And then we end up with this type of equation for the Kz equals to half of the gravitational wave frequency. Kz is the mode of the electromagnetic field. And then we have this made. Yes. So the CS will be. Yeah, so we consider like you have a medium with some refractive index, and then the speed of light will be smaller. Yeah, well, the name is not usually CS, yeah. It's like the refractive index over the other. For some reason in the literature, people call it CS. So, but then we have this matrix equation here, where here we have the free components. But we know that, well, photons only have 2 degrees of freedom. So in order to decouple them, we multiply them by this matrix here. And then we end up with this equation where Y has only the 2 degrees of freedom of photons. These quantities are gauge invariant. And here we have the new friction matrix and the mass matrix. And then what we see also in this case is that now instead of the gravitational wave being amplified, the gravitational wave is what generates the oscillation in the mass term. And then the 2 degrees of freedom of photons are amplified. So here you have a conversion from the gravitational wave to the electromagnetic field. Here with CS1, we are in vacuum. And then in this case here, the resonance does not happen in the first resonance band. So it's not very efficient. And then this one is in the medium, where this is the refractive index of water, which is very large. So here we see that we reduce this from 10 to 6 to 10 to 4. So you can reach the same amplification in a much shorter time because you are in the first resonance band. And here you have the Y and Z in orange and blue. So we see that both components are amplified because of parametric resonance. So here we see that there is indeed a resonance between a gravitational wave and an electromagnetic field if they are in a medium. It could be, for instance, the intergalactic medium, but then it's possible that you do not reach the first band. So the amplification would be very slow. So this is one of the main problems of this scenario, which is you need a very high refractive index and you need to wait for a long time interval. So in order to observe this in an astrophysical system, it will be very challenging. Oh, do you have questions about this part? Okay, so the next part was another bound scenario that I considered recently. with some external collaborators. So what we did was to consider Wheeler-DeWitt quantization in the de Broglie-Bohm approach to quantum mechanics. And then what we do is to consider a non-unitary propagator, which is going to propagate this initial wave function, which is an ansatz. And then we considered a Gaussian wave function with a momentum in the configuration space, so that we could create an asymmetry in the bounce that is generated. What I mean by asymmetry is that the contraction phase is not the same as the expansion. So here we have a contraction phase that could be almost Minkowski, and then after the bounce, you have something that is very accelerated. And then this is the scale factor that we obtained, where y is the parameter that controls the asymmetry of this bounce, and it's related to the momentum of this Gaussian wave function. And what we realized is that if you consider this y to be very large, what happens is that you have here almost Minkowski, and then you have the bounce, and then naturally you reach almost the Sitter phase, which could mimic inflation without any extra field or without reheating after, and also with a graceful exit. So we decided to look into it further and see if it would be also in agreement with cosmological perturbation theory. So here we have the Muhanov-Sasaki equation, and here we plot this potential here, just to see when these modes would cross. And of course, we are interested to make them cross in the almost the Sitter phase, so that we have the compatibility with CMB data. So we want them to cross here. And here we have the usual classical phases, both for contraction and expansion. So we thought this would be interesting because you solve the singularity. You don't have an extra field in order to realize inflation because it appears just due to quantum effects. And you don't need reheating because all of this happens in a radiation-dominated universe. So you already go into the early radiation domination naturally without the need to reheat or anything.
Because it said that after bounce you have this phase. But in order to enter this phase, you need to have some kind of cosmological form, whatever. So how does cosmological form emerge?
Yeah, so it appeared because of the quantum effect. So this the Sitter phase is still quantum. It's not classical yet. And this comes from this scale factor that you have. So if you perform an approximation where this y is very large, but the time is still close to the bounce, you can expand this expression, and then you reach that A goes as the Sitter, usual the Sitter phase. So it will be due to quantum effects and not like an inflaton or... And then we went to the perturbation level and we computed here. Well, here's the numerical result that we have for this Muhanov-Sasaki equation here for a very large value of the y variable in such a way that we have this almost the Sitter phase. And here we see the mode outside the horizon, which is frozen, and here it enters the horizon and decays. And then we are interested in this part here, which is the part that enters in the computation of the power spectrum. These prefactors are just like normalizer factors and so on. And then we put this Muhanov-Sasaki variable here. And this is the result that we have for the power spectrum. So here we see this scale invariant. In principle, it's almost scale invariant, but it's so close to the Sitter that the spectral index is very close to 1. And this would be the first problem of this scenario. It's too close to the Sitter. The spectral index is not 0.96. So in order to do that, you would have to deviate a bit from radiation, because here we consider just radiation, omega 1/3. So in order to achieve this spectral index compatible with observations, you would have to deviate a little bit from radiation. So like a 1/3 plus or minus epsilon. And then here we see that we are able to achieve the correct amplitude for the perturbations. So this part is okay, it's consistent. And then the other problem is when we compute the tensor power spectrum, which is similar to this one, because like the equation will be the same for the tensor modes, except that the CS will be 1. So for the scalar part, it's 1/3, and now for the gravitational wave, it's 1. So it's like the same equation. It will lead to a similar amplitude. And also we have a 2 factor in front of the tensor power spectrum because of the 2 tensor polarizations. And then the tensor to scalar ratio gets too high. which is completely excluded by CMB data. So these two problems, they are relatively serious, but in principle, they could be solved by the same thing, which is to consider a curvaton field. So this is one of the last projects I've done during the PhD. So now as a future project, we want to add the curvaton field, which of course you lose simplicity because the idea was that you had inflation without an inflaton, which was very interesting. And now you have to add another field to solve these problems, but at least you still keep graceful aesity, no singularity, and no reheating. So there are still some interesting aspects in this scenario. And also another possibility is that you could have a different theory, because here we use the Wheeler-DeWitt quantization, but maybe if you can find an asymmetrical bounce in another type of quantum cosmology bounce, maybe you can still make this type of asymmetry in such a way that you generate this quasi-de Sitter phase, and then you can maybe evade these issues that we have in this approach. And then I think this is the last part. Okay, I think I only have 2 slides for this, so it's okay. So here I have this scenario, which is called holographic dark energy, which was a proposal of dark energy, which is inspired by the holographic principle. So the idea is that you have an energy density in the bulk, which is the energy density of the cosmological constant or dark energy. And then you are going to relate it to the area of the boundary around it. So this is mainly the expression that you have, where this is the area of the boundary, and this is the density of this dark energy component. This term is a term that appeared later in the literature. So this was the first proposal, just this part. And then my co-supervisor in Krakow obtained this covariant action for this theory, which hasn't been obtained before. And it looks like this, where these Z and ZAB and so on, they are related to Stuckelberg fields. So here we have this time-like Stuckelberg field. And then in the Z's, you have the space-like ones, 3 of them. And then is the way to write the theory in a covariant way. And here we have an inflaton, because what we wanted to see is whether you can have this holographic dark energy and still keep inflation without spoiling the accelerated expansion. And here we obtain the equations of motion. And then we see that we have this energy density here, which has the holographic component, which is responsible for the expansion. And this part, which, because it goes as h to the -4, it's like a dark radiation. So first at the background level, we checked that the inflaton always dominates the other components. So at the background level, it does not spoil inflation. And then at the perturbative level, it's the same. So we computed the scalar power spectrum, the tensor power spectrum, and there are some additional terms, but they decay very quickly in the very first E-folds of inflation. So they do not represent any type of problem from the observational point of view. And here we have also the spectral index, which also depends here on this extra term. It's related to the mass of the graviton, because this effective field theory is a massive gravity. And so what we conclude is that holographic dark energy is completely compatible with inflation, so it could still be a valid candidate to explain dark energy. So that's it that I would like to talk to you today, and thank you for your attention.
We have already some number of questions during the talk. Questions? Okay, so I understand that everything was clear. Thank you very much.
Thank you.